All right, guys, so glad that you had a little quick conversation about that. I'm going to talk about, there's not a sub in another teacher's class, but I have a teacher watching until the sub comes. It's in Miss Lewis's class. She's the farthest away from me on the corner. Yeah. Go to the office and say, Miss Lewis does not have a sub. That's all I need them to know. Thanks. Okay, so just trying to help out another class, make sure that they know what they're doing. So we have a couple of items to discuss today. The driving forces reactions are two. You guys took your notes on those last night on your, pull those little papers out of our usual class. We have this nice chart, and you should be able to determine which type of forces are favorable for a reaction to actually occur. Zach, give me one of the driving forces of reaction. Entropy. What is entropy? A measurement of, anybody? Mikado? Disorder, right. So this is a measurement of disorder. And so if you had to speak of, a state of matter that was very disordered versus one that was very ordered, Isabella, what would you say would be very ordered as a state of matter? Solids would be more ordered than gases for sure. So entropy is just a word that means a measurement or a level of disorder. And so when we're talking about this, it's really in respect to states of matter or number of moles of particles. So in this case, a solid is less disordered than a liquid, which is less disordered than a gas. And that's just based on their relative positioning of each other. So solids are really tight and compact like this, whereas gas is bouncing around crazy. It's bouncing off the side of the container and so forth. So, Ashton, tell me the other force of reaction. Enthalpy. So this is number one. Enthalpy, or enthalpy, is sometimes how it's stated. And that's referencing the measurement of what, Caleb?
The measurement of energy.
Okay, the measurement of energy. What kind of energy?
Potential or kinetic.
I'm pretty good with that. I'm going to stick more with kinetic. Can somebody describe that in one other form? Yeah. Heat energy or thermal energy. So kinetic energy, heat, and thermal energy are all actually really, really related. So I'm really cool with either of them. But measurement of thermal energy, and that might give us a little bit more context. So we actually dealt with different forms of enthalpy before. Yesterday I showed you guys the demonstration with the hydrogen peroxide. It decomposed and there was that steam coming off, and I said it was wet around it. It was steaming, so what kind of temperature do you think I was feeling? Hot. And you guys told me it was what kind of reaction? If it was exothermic. So you actually know the two versions of enthalpy, exothermic and endothermic. So with that in mind, the only weird new thing is entropy. And so these are two forces that force a reaction to actually occur. So remember yesterday, or a couple days ago when you were doing your NIE lab, it was like, will a reaction occur or will it not? And you had to say yes or no. That's actually you looking for a chemical change, and some of those things were solids were forming, gases were forming, energy was being given off. It was just forces of chemical changes were occurring. So with these two, there are two versions of each. Entropy and enthalpy. Entropy can either increase in disorder or decrease in disorder. Those are our two versions. What's the symbol for entropy? Delta S, right. So either you can have an increase in disorder, which is an increase in delta S, that's a positive increase. And then, actually I won't put positive there, I'll conserve that for denoting enthalpy. And then you can have a decrease in disorder, which would be a decrease in delta S. Either way, the reaction possibly could still occur, but there's some other conditions you must consider. Enthalpy, what are the two versions? You just told me this. Yes, exothermic and endothermic. So exothermic has a delta H. That's what sign? Positive or negative? Negative, good, because it's releasing energy. So the energy is being removed from the system, so we're subtracting it, which is why it gets a negative sign. Endothermic, the delta H is positive, and so that's saying energy is going into the reaction. So which of these feels warm to the touch? Exo, right? So this one's just going to feel warm to us when we're holding it. So a good example of that might be a hot pack or a test tube that's releasing energy. You feel it, and like even coffee, holding a coffee cup or holding something that's warm to the touch would be considered an exothermic process. So what would you feel for an endothermic reaction? It would actually be cold to the touch. So what's happening is your hand, let's say I have an ice pack, okay? And you're holding it, this arm, I'm holding in a mitten. Okay. Pretend the mitten's not there. Okay, now we have fingers. Okay, now we're a bear. Okay. So at this point, our ice pack is cold to the touch. But why? We're taking heat from where? Our hands, right? There's a system, which is this right here. This is the system we are talking about, looking directly there. But then everything else is considered a surrounding. And so our hand is surrounding that. And so there's this energy flow into the system. And, you know, if our hands, the surroundings, it has to come from us. And so we feel the cold because we're lacking heat. And vice versa, if you have a, say, hot chocolate, and you're holding your little mug of hot chocolate, and you know your hands here. Put a little bear paw on this again. Okay, there we go. Holding your hot chocolate little thing. I know I'm an artist. I'll take autographs later too. Okay. So in this case, the hot chocolate is the system, but it's exothermic. So where does it? What's happening here? Releasing heat to your hand, and then sometimes that heat's a little bit much, and then we drop the coffee and it goes everywhere. Okay, but our hands have these sensors that say, hey, this is too hot, you're gonna die. Or, this is too cold, you're gonna die. It tries to take care of you. So there's sensors in your hand that connect your nerves to your brain and go, this is not good for your survival. So we have both scenarios, and we've dealt with these before. Now the only thing that's weird is the whole entropy thing. So I have a quick video for you guys on entropy, and then we're going to go into reaction stoichiometry, which is why you need your calculator. So let us write down a couple of things that you hear on this video. And this guy, Bozeman Science. I'm going to just have you guys watch the first little bit of this because some of it's very repetitive.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 57. It's on entropy, which is really the dispersal of matter and energy. So imagine I had a little bit of milk in a glass and I were to spill it. I will have increased the entropy of this isolated system. And there's an old saying that you shouldn't cry over spilled milk. I totally disagree with this. You should cry over spilled milk. And the reason why is it's an irreversible process. In other words, it's not just going to magically move back into the glass. You've increased the entropy, and it's going to take a lot of work to put it back where it was. And so entropy in AP chemistry is not something that you'll have to calculate. You have to understand it qualitatively. In other words, you have to look at a system and figure out what's happening to delta S. And so what is delta S? That's simply the change in entropy over time. Now, what does this little degree symbol stand for? That means that we're measuring it at standard temperature and pressure. And so if we were to look at a system, we should be able to make predictions about what's happening to our delta S. And that's what I hope you can do at the end of this. And so if we define it, it's simply dispersal. Dispersal of matter and dispersal of energy. So what are some examples of that? Let's say we were to make some phase changes. We were to go from a solid to a liquid to a gas. What would we be doing? We'd be dispersing or moving that matter away from its center point. And so we'd be increasing the entropy. In other words, our delta S would be a positive value. We'd make that matter dispersed over time. We also could do that by stoichiometry. In other words, if I look at the moles before a chemical reaction and the moles after, if I have more moles after the reaction, I've increased the entropy. And also, if we take a gas and we increase its volume, we're moving those molecules apart, and so we're increasing entropy, or delta S is going to be a positive.
So he said phase change, which is the least, which has the most disorder of the phases? Gases. He said stoichiometric products. He said count the moles of products, like moles of gas of products, because that means if you have more gases, more disorder. And then he said gas volume. How did that relate to disorder? He said what in volume? Increases or decreases? Which one? Increases, because basically very compact things can't move around a whole lot. Their disorders kind of compact and low. But the bigger spaces they have, the more positions they can take. They can bounce around in more areas. They just have more places to play, so they have more disorder as well.
Positive value. Now let's say we look at energy. How could we disperse energy? Well, by increasing temperature. If we increase temperature of gas, according to the kinetic molecular theory, we're spreading that energy out and we're increasing entropy. Now entropy is a term that people really struggle with, and so I wanted to start with a good example. And so I've got two videos here, but they're the same exact video. It's just that one of them is played forward and the other is played backward. And so your goal is to figure out which one is forward. So let me start playing that. It's just going to loop over and over and over again. And so your goal is to figure out which one is forward. Have you decided yet? The right answer is A, but that was kind of hard. Let's look at another one. I've got a little pendulum here, and let me play this video again. It's the same video clip. It's just that one of them is played forward, and the other is the same clip. It's just played backward. Have you figured out which one is forward? There's some clues in here, but the right answer is B. Let's look at the next one. It should be a little easier now. So if we look at the next one, I'm going to play this again. So again, same video, one is forward, one is backward. Hopefully you figured this out. The right answer is B is being played forward, and A seems somewhat magical. It's being played in reverse. Let's look at the milk. So if we look at the milk right here, which one is being played forward? Hopefully you figured this out. A is being played forward. Okay, and so why did I do that? Well, what we're looking at here are irreversible processes. In other words, if we play it in this direction, it's irreversible. In other words, it's impossible for it to occur in the reverse. Now, it's not totally impossible. That could occur, but it's statistically improbable that it's going to move in the other direction. And so that direction is really important when we start to talk about entropy. Because what happens during an irreversible process is that we're increasing the entropy or the dispersal of that system. And it just doesn't move back, and that'll become really important as we talk about the next few videos. And so the second law of thermodynamics says that in an isolated system, or a closed system isolated from the universe, entropy never decreases. In other words, our delta S is always going to be positive. In other words, matter and energy are going to become dispersed over time. In other words, randomness increases over time. Now, you might think to yourself, I know that's not true because I see stuff out there that's not random. In other words, I see trees and cars and DNA, and I know these things have a high amount of order. Well, you're not violating the second law of thermodynamics because remember, we're talking about an isolated system. And so we can decrease entropy in an isolated system, but as we do that, we're increasing entropy of the surroundings or the universe around it. And so again, to define entropy, what is it? It's simply matter dispersal or matter spreading apart. And so let me give you an example of a certain type of matter dispersal would simply be phase change. So as we move from a solid to a liquid to a gas to a plasma, that matter is moving farther apart. And so as it's doing that, what we're doing as we move from a solid to a liquid to a gas is that matter is spreading apart, and as it does, we're getting a delta S, which is going to be a positive value. Now let's look at stoichiometry. You should be able to look at an equation like this and immediately figure.
So from this equation, this was kind of what you're doing on your video portion towards the end. Okay, first off, let's name the reactant. Name it. Yes. Dinitrogen tetroxide yields nitrogen dioxide. This is not an ion, so you can't say nitrite or nitrate or anything. It's just the normal covalent name. So with that, okay, so you know your naming. How many of each do I have? Reactants? Whoa. Hold on. No, not actually. Let's go back. How many moles of dinitrogen tetroxide do I have? What's the coefficient? 1. There's one of these molecules. One of these molecules is reacting, or decomposing in this case, to yield 2 of these molecules. So think of them just as molecules in themselves. So if I have one gas molecule yielding 2 gas molecules, what do you think happened to the entropy, aka disorder? It went up because I had one little consolidated gas. Now I have 2 molecules of gases. So there's more disorder because there's more moles of gas. All right, we're going to keep using that kind of logic.
Figure out what's our delta S. Well, how do you do that? So if we've got our reactants on the left side and our products on the right side, we have 2 moles on the right side and only 1 mole on the left side. If we show you a picture of that, it looks like this. So we have dinitrogen tetroxide and we're making 2 moles of nitrogen dioxide. And so what are we doing? We're increasing the entropy. You try the next one. So if this is our equation, so we're taking liquid water and turning it into gas, hydrogen gas and oxygen gas. What's happened to the number of moles? Well, we've increased that. So our delta S is going to be a positive value. We're spreading that matter apart. Now there's another clue here as well. We're going from a liquid to gases, and so we really are increasing the entropy of this system. Now let's look at gas volume. As we increase the volume of a gas, so if we have a known quantity of that gas, as the volume gets larger and larger and larger, the matter is spreading apart, and so we're going to have a delta S that's going to be a positive value. So not only is entropy dispersal of matter, it's also dispersal of energy. So if we were to look at this Maxwell-Boltzmann distribution of...
A little later in our lives together. together. Okay, so before we move from there, I will give you guys a taste of entropy and entropy together once again. I just want to make sure we understand. The right one, sorry. So I want to make sure we understand how to predict if the reaction will occur in the forward direction. So he mentioned the whole irreversible process. That basically means it's really unlikely for that process to reverse, like the buildings to rebuild themselves, right? So basically what that means to us is that we are talking about the forward direction, so we were saying which forces behind the scenes actions are going to force that reaction to happen in the forward direction only. So we're looking for forward direction only. That's what we always read from right or from left to right reactants to products. So this is one of the examples, states changing and the number of moles of gas increasing to show that increasing disorder. So one of the ones from your notes from yesterday, I'm just going to give an example like sodium chloride solid yields sodium plus chlorine, and these are aqueous. And what if I put 100 kilojoules, which is a form of energy, on the reactant side? First off, you should be able to identify delta S and delta H. Let's start with delta H, which is enthalpy. Is this representing an endothermic or exothermic reaction? Why endothermic? Right. This means requires energy. And so that's going to be a positive value, which is endothermic. Okay? And then the state of matter is changing from solid to aqueous. What do you think is happening to disorder? Why increasing? Yeah, really well-structured solid to this crazy-looking like liquid aqueous solution. So this is also going up, so it's positive. So that disorder is increasing. Okay, so now I wrote happy faces and sad faces, right, to show you like which ones are favorable. Is this increasing disorder favorable or unfavorable? Favorable, right? That is a good thing. The universe wants it. We're satisfying the second law of thermodynamics. The universe wants more disorder overall. The endothermic nature of this one, yay or nay? Nay. Normally, we want reactions to release their energy. We want them to get more stable, so they release their energy, which is exothermic. That's not the case here. So this would be like sometimes favorable in the forward direction. It depends on the temperature. So it will depend on temperature when you have one happy phase and one sad phase, or one favorable action and one unfavorable action. And we'll work with that a little bit more probably after next week. Okay? So, get a stretch break in because you guys are sleeping on a Friday morning. I want you guys to talk about reactions or your project or your, I don't have it on my board anymore. You guys have the back of your sheet, chemical reactions performance task. Okay? I had to switch a couple group members, so I'm going to give you guys about 2 minutes to talk. But I need to tell you who I want in a group first. So I have Isabella's group, you're intact. Ashton, Megan, you guys have Jacob, because I had to move him. Caleb, your group's intact. With Cassie, you're with Caleb's group. Meredith, Sydney, Syrian. Lauren, Caitlin, Ansley. Zach, Avery, Ishmael. Omar, Frank, Will. And then Shelby, Sophie, and Bradley. Get up and talk. Get up and talk. And then remember, you're talking about this. Bye. From yesterday, we didn't get to tackle it yet. So, you have this in the back. Here, hold this and give it back to her. Back to you. Oh, Ishmael Avery. Okay, so yeah, you should be talking to them. All right, take one more minute. Next week, I will have you guys start your video process. So if you didn't get to start yesterday because you were working on problem set forever, then you got a little bit more on your own time to do. But in terms of what I need a Google Doc with your information. I will say yay or nay to the reaction you've selected along the lines of safety concerns and I have the materials and it makes sense to do in fifth grade classroom. It's one of our 5 cluster reactions. There are some requirements, but I want it on a Google Doc so I can actually give you feedback in like real time and everybody can see it. So I'll try to give you guys some time to do it at the very end of class, but at this point, I just want to make sure you guys touch base with each other for completion for third quarter. So finish talking about what you need to talk about. Another 30 seconds. Why would you bring that up knowing you're changing? You're changing. Bye.
So, is this supposed to be like a real-time video, or are they doing edit?
Yeah, okay. Broadcasting's like, yeah, I got you. All right, so write this down for me on the board. Write this down. And I know that a couple of you have assignments to turn into me. Just hold it till the end of class because we'll have a couple of chances to practice together. My goal is to give you 3 healthy, full examples of the process we're going through today. So basically, we're pulling together balanced chemical equations. So synthesis, decomp, single, double, and combustion. And we're going to marry it to the mole relationships. And so I kind of gave you a preview to that because we were talking about, so many moles of this react to make so many moles of this. So we were talking about moles, and moles, but really what we were looking at on that example, he had nitrogen or dinitrogen tetroxide yields 2 nitrogen dioxide. That was his example, right? And I was like, 1 molecule and 2 molecules. What was I looking at to get those numbers? The coefficients. I was looking at the coefficients because that told me the recipe for this reaction. The recipe is if I take 1 of those, I can make 2 of those because that's just how the nature of the reactions work. There, it's already balanced. That's giving me the ratio or the recipe. So just like a recipe at home. If you want to make 24 cupcakes, you better get 2 boxes of the cupcake mix and 4 eggs and a cup of milk. So we have to follow this recipe to make something happen the way it's supposed to happen. And so just like in cooking, we will see the same thing as there's numbers associated with how many of each of the reactants you want to make the products you want to get. So I'll go through a recipe example with you as well. But these little numbers, which we've been calling coefficients, we were using them to balance our reactions. But now we're going to use them as a comparison and go, for every 1 of these, I can make 2 of these. And so I'm intentionally saying the word these because I want you to know that you can really call it, 1 molecule, 2 molecules, or 1 mole of that versus 2 moles of this. Because a mole is just a number, right? So I could say this was 1 dozen, which that really means what? 12. And I could call this 2 dozen. And that really means 24. So that word dozen, it means 12. So when I say mole, that really means times 10 to the 23rd. Ain't nobody got time to say that every single time. So we just say mole. Okay? And that's just indicating that we know there's a number behind it. So we're marrying balanced chemical equations to mole relationships. So remind me one more time, what are mole relationships? So you have your mole map in your head memorized. Sophie, what's the 1 mole related to on the top branch? Sophie? The particles, and then Avery, particles is related to mole how? Avogadro's number, 6.22 times 10 to the 23rd. Lauren, what's the middle branch? Grams, and how do we relate grams to moles?
The number of the periodic table.
Right, so periodic table, molar masses, we take those and go. Frank, what's the last one?
Volume.
Volume, how do we relate volume to moles? Say again?
24.
22.4 liters per 1 mole. Everything is related back to this 1 mole. So far, we haven't really converted from reactants to products. We've only said, okay, if I have 5 grams of oxygen, how many moles of oxygen is that? If I have 6 grams of sucrose, how many atoms of sucrose is that? And we've been writing one particular thing from here on, or from before now. Now we're going to be writing 2 different types. So it's just pulling 2 things together at this point. It's not too bad. So here's like just an example of what we've been doing. 2 hydrogen molecules, what I would say for that, plus 1 oxygen molecule yields 2 gaseous molecules of water. So that's us just reading the reaction and noting that they're molecules. And why am I saying the word molecule? Because they're what? They're all covalent here, right? Well, I could also, like I just said, say it like this. 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. Because I'm just saying the relationship between them. Because really, what's the relationship between molecules and moles? Avogadro's number, 6.022 times 10 to the 23rd. And I'm not going to say whatever 6.022 times 10 to the 23rd times 2 is. We're just not going to say that. We're going to say 2 moles instead. So there's many ways to describe this. All right, so if we're dealing with gases, which in this case we are, we could also call them liters. So 2 liters of hydrogen, 1 liter of oxygen, and 2 liters of water. Because how does the mole relate to liters? 22.4. And they're all related in the same way. And that's why we can just say mole instead, because it's so much easier to say mole. And plus the mole connects to every other unit. So it's a great stepping stone to get across, which is our goal in that case. Question? You guys good so far? Okay, so this is just setting you up for success to see that there's this ratio here. So the ratio, 2 to 1 to 2, what am I looking at to get those numbers? Coefficient. So we will now start to call, anytime we do a comparison between a reactant and a product, or even a product and a product and a reactant and a reactant, if I'm comparing 2 things, I'm going to start calling that, instead of like a coefficient ratio, we're just going to call it a mole ratio, because technically everything can be related back to the mole. And so that's what you'll hear me say from here on out, mole ratio, mole ratio, mole ratio. We just have to have a balanced chemical equation first, and we're good. We're good to go. Okay, so with this example, I can look at hydrogen, it's balanced, I have a 2 there. I can look at oxygen, I see it's balanced, I have a 1 there. The mole ratio is a 2 to 1 ratio, or 2 moles is equivalent to reacting with 1 mole of oxygen. And so we start to write them like this as just noting their equivalencies. And I know those aren't equal, like not truly equal, but like I said, if I say 2 dozen, you know that means 24. So it's just us saying that something is considered an equivalency. So before, when we've had 2 equivalencies, we know that they're equal or equivalent. How have we always written them like in a process? Like in a conversion process? Say again? Mm-hmm. I mean, everything that we write as a conversion factor is considered an equivalency. Like 1 mole equal, or like 1 mole of hydrogen equals how many grams of hydrogen? 1 mole of hydrogen, 1.01 grams, right? And I could say 1 mole of carbon equals how many grams of carbon? 12.01, because you're looking at the periodic table. So this is considered an equivalency, but how have I been writing the other stuff? Yeah. Yeah, top and bottom as a fraction. So we're going to write these as a conversion factor, as a fraction. So 2 moles of hydrogen is equivalent or equal to 1 mole of oxygen. And so I could write it top and bottom like that, or I could flip it. It really depends on what I need from this conversion. So remember, if they're equivalent, they can be written as a fraction like this. And that's going to be called a mole ratio from here on out. All right, give me a thumbs up if I'm good to go. Most of us looking good there. Okay, so look at this one. Calcium plus, name that one for me. Name that guy. Iron 3. Permanganate yields calcium, permanganate, and iron. What kind of reaction is that? Say again? Single calcium and iron switch spots, okay? So, John, what is the mole ratio between calcium and iron 3 permanganate. So it's the mole ratio between calcium and iron 3 permanganate. Look on the board. All right, no, you're with me? You can stand up at the lab station if you need to. So tell me what you think. No, so the ratio is going to be a number and another number. So what's the coefficient for calcium? 3. 3 moles of calcium is equal to, what's the coefficient for iron 3 permanganate? 2 is equal to 2 moles of iron 3 nitrate permanganate. So we can say they're equal like that, or I could just write a ratio as 3 moles of calcium is equivalent or is reacted with every 2 moles of iron 3 permanganate. And so when they're in a balanced chemical equation, we're actually saying I need 3 parts calcium to react with 2 parts iron 3 permanganate to make 3 parts calcium permanganate and 2 parts iron. So it's just a ratio that's we're considering like a recipe. So I could do about, let's see, 6 or so ratios. 3 moles of calcium equals 2 moles of that. 3 moles of calcium equal 3 moles of calcium 3 permanganate. 3 moles of calcium equal 2 moles of iron. And that's just with the calcium, right? What else can I do? I can do what? So the iron 3 permanganate relates to calcium permanganate, so in a 2 to 3 ratio, or iron 3 permanganate, 2 moles of iron 3 permanganate relates to 2 moles of iron. Okay, or what else have I not compared? Calcium permanganate to plain old iron in a 3 to 2 ratio. So you can see you can come up with about, depending on how big the reaction is, probably 2 to 8 different mole ratios just because you can compare so many things at a time. But we're only ever comparing 2 things at a time, so we can't compare more than that. Okay, so we're going to use our balanced chemical equations as we go through today. And I'll keep reinforcing that mole ratio aspect. All right, so on this one, how many different comparisons can you make? Frank, give me one. Hydrogen peroxide, I got you.
Hydrogen peroxide to oxygen.
Okay, so that's going to be 2 moles of hydrogen peroxide for every...
1 mole of oxygen.
Right, and there's a 1 here, as you can imagine, 1 mole of oxygen. Caleb, give me another. Oh, Caleb, sorry. I'm looking at both of you guys in mine. Caleb. Beautiful. And so this isn't too hard if you're noticing you're just looking at the coefficients, right? One more, Shelby, sorry. So we did this one to oxygen and we did this one to water. What else can we compare? Of water to what? The last one, 1 mole, right, there's a 1 there, 1 mole of oxygen. So these are all called mole ratios, and they help us get from one reactant to another product, or from products to products, or reactants to reactants, it depends, but we're just basically comparing 2 things, that's it. Nothing too crazy here. All right, so we're going to use this in context now on a reaction. We're going to do some conversions. So this is not the exact one. Here it is. Okay, you guys have this on the back of the notes you took last night. Find this now, and I'm going to show you how you actually know 95% of this already. You already know it. So let me show you from a different perspective. Let me see if I can rotate this. So here we go. We're going to make this super duper big. Okay, so this is your mole map, right? Moles can be related to, and I know it's in a different order because I just turned this thing. Moles can be related to particles through Avogadro's number. Moles can be related to volume through what constant? 22.4. And moles can be related to molar mass, or grams through molar mass. The only other one we're going to deal with later, oopsies, later today is this molarity thing. So this one is new. We'll get to that in a second. Volume of solution. So you already know this, okay? So what we're doing now is we're connecting this to another identical one like this, but we're connecting them with a mole ratio in between. So that's what this is. So all of this you already know. Actually, on the bottom you already know. These are just mirror images. I've connected the moles to moles, though, with our balanced chemical equation, which is our coefficient, which we call the coefficient comparison a what? Well, coefficients compared, we've been calling it a mole ratio. Sorry, I thought I heard that. So that's called a mole ratio. So if I ever want to get from, let's say, moles of hydrogen peroxide, like that last example, and get to moles of oxygen, I have to go through the bridge of the mole ratio, because everything else is easy. We know how to get from moles to anything else. It's just how do we get from moles to moles. That's been our problem, and we didn't ever have to do it, but now that's our new solution to that problem. We're going to use this quite a bit, so make sure that's in front of you. Okay, so we'll keep referencing this as we go. All right, so this is the first example on your reaction stoichiometry, which is right next to your mole map. You guys see that? Synthesis of aluminum oxide from its elements. We've done this before, actually. So whenever you're solving problems that are called reaction stoichiometry, reaction, it has to kind of be that first thing you hear, right? So I have to have a reaction. Step 1, write reaction. Step 2, write out givens. And question, or, you know, like the unknown as we've kind of termed it before. So we're getting back into the math side of things. We kind of took a break from math, we did our reactions, and we're going back to the math side of things. So, what's aluminum oxide, guys? AL what? Al2O3. Thank you. Al2O3, because you're crisscrossing your charges. Okay, from its elements. It says synthesis of that, so that's why I made that a product. From its elements, what does that mean? From Al and how do I write O2? Okay, is that balanced? No. Go ahead and balance it. I'm ready when you are. 4 moles of aluminum for every 3 moles of oxygen to make 2 moles of aluminum oxide. And so I'm going through balancing a little quicker because that's our old news to us. So you heard me say 4 moles of aluminum react with 3 moles of oxygen to make 2 moles of aluminum oxide. That could be like 3 eggs or 4 eggs and 3 cups of flour make 2 awesome cookies. I don't know, or cakes. Cooking, yeah. All right, so we have our balanced chemical equation. Check. Now let's look at the questions here. This one's just making sure you understand how to write mole ratios. So, what mole ratios can be derived from the balanced chemical equation? Megan, can you give me one? You can pick whichever ones you want to pick. 4 moles of aluminum.
Over 2 aluminum.
So she chose a reactant and a product because that's nice to kind of go between the two. I already give me another.
3
Moles.
over 2.
Okay, and Avery, give me one more.
3 moles.
So we went from here to here and here to here. What else have we not compared? Yeah, so I can go back. That's cool. I don't have to go like from front to back and go back to front. So this would be 4 moles of aluminum on the bottom. Okay, so you guys just told me one and we wrote over the other. Remember, these are all flippable. All conversion factors are flippable. So you could flip them. It depends on what you need to do for the cancellation of units. So they're very flexible. You can use them however you need to. All right, so now we have to write down our givens. In part B, how many moles of aluminum are needed to form 2.3 moles of aluminum oxide? Sounds like a big question, right? Break it down to baby pieces. What's the given unit or thing we have to start with? Okay, so write down given. Literally write down the word given so you get a couple of good examples in. And you can go back and look at your notes and actually understand what you wrote down. So given 2.3 moles of what? Al2O3. Okay, so that's our given. What's the question? What does it want to know? Oh, so unknown, or the question is moles of plain old aluminum. And this is referencing that reaction above. So I'm going to make, do you guys have your reaction? I just need a little bit of space here. Okay, so I can see that I have to start with this. There's no way, I don't have a conversion straight from moles of aluminum to, moles of aluminum oxide to moles of aluminum. I don't have a straight conversion between those, because this aluminum oxide is talking about this guy, and this aluminum is talking about this guy. So I have to see there's a relationship between them, and that's called the mole ratio, the Balanced-Chemical equation. So I start off with 2.3 moles of aluminum oxide. Okay, on your mole map, where are you at? So I'm on this huge mole map here, and now I'm doing the combined one. I'm going to call that moles X. So when you touch moles X, and you want to get to moles of Y, which is something else, what do I have to do? Just the mole ratio. This is a single-step conversion. What is the mole ratio between aluminum oxide and aluminum? Hold on, I hear you. Say it again. 4 moles of aluminum for every 2 moles of this. You are looking at the coefficients, you're pulling them down here. Who goes on top? 4 moles of aluminum, because that's what you want, right? You want the aluminum at the end. Who do you want to cancel? The aluminum oxides. So that 2 aluminum oxides are going to go on the bottom. 2 moles aluminum oxide. Because this first unit guides you and tells you what goes on the bottom, just like we've been doing for all of our other mole stuff. So these moles of aluminum oxide cancel, but the numbers remain, so now we just have to calculate. That's why you have a calculator. Yeah.
Can't you just multiply like it by 2 because
Well, yes, but the process of making sure you know your mole ratio, like how do you pull the information from here, leaving it like that makes you know what you're doing. Yes, and Andy would this multiple. How do I do that? Answer? What? 4.6 what? Moles of aluminum. So I'm going to keep asking you moles of what, because I want to make sure that you've actually seen the conversion, that you went from apples to oranges. You went from one thing, you canceled that out to whatever remains here. All right, that was a single stepper, because we saw we were in the middle of the mole map, and we just had to do one step from the Balanced-Chemical equation. Next one, what is my given? Say it loud and proud. 0.84 of just plain old Al aluminum. And it says, how many, what's my question? How many liters of, how do I write oxygen according to my Balanced-Chemical equation? O2. And it says that STP. That's just reminding you that the whole conversion with liters has to be at STP, standard temperature and pressure. Don't worry about that right now, though. Okay? So I see my given, I see my question. I see I'm going from apples to oranges. I have to go through the bridge of mole ratio eventually. So I start off with my given, start here, 0.84 moles of aluminum. Where am I at on my mole map? I'm at moles of X. Okay, if I'm at moles of X and I want to eventually get to liters, I might scooch back real fast just to show you this on the bigger slide, because this is a little teeny tiny thing over here. So remember, we're at moles of aluminum, we want to go to liters of oxygen. So we're at moles of aluminum. I don't want to go to liters of oxygen. Where's that at down here? So down here. Okay, so we're going to go from moles of aluminum to just moles of oxygen first, using my Balanced-Chemical equation ratio. Then we'll go from moles of oxygen to liters. How? 22.4, and I'm down there to volume of gas. So how many steps is this going to take me? 2. And this is the new one that we're using more today. Okay, so here I have my moles of aluminum. You guys told me you have to have your ratio. You have your equation on your paper. Mine's way up here on the board. How many moles of aluminum are in the reaction? 4. Where do I put moles of aluminum? Bottom 2. What do I cancel out moles of aluminum? Good. And I'm going to oxygen, so what's my mole ratio for oxygen? a 3, and that's because the balance chemical equation said so, right? So just put BCE above that if you forget where those numbers are coming from. Okay, so far so good. Moles of aluminum cancel with moles of aluminum. Now I'm in moles of oxygen, and you guys told me you knew how to get from moles of oxygen to liters of oxygen. You know there's a direct connection. What is it? What do I write the 22.4 at? On the top, 22.4 liters of oxygen correlates with what? 1 mole of that oxygen. Do not bring this 3 down here. This is just saying I have a ratio of 3 to 2. It's that unit you're looking for to say I need to cancel. Because this aluminum canceled, this mole O2 will cancel and leave me with what? Liters. So moles of O2 cancel there. So math it up. 0.84 times 3 over 4 times 22.4. This is why you have a calculator, so you make sure you're putting your calculator right. Yeah, because I'm going to be honest. Some of you guys didn't get answers correct in your quest because you didn't practice in your calculator enough, or at least the little blue ones, the evil blue ones. That means you have the double parentheses and so forth. You got everything math process right, but then you put something wrong on the calculator. It's pretty lame. Make sure you're putting stuff in your calculator right. From this 4 and this 3 came from the balance chemical equation, which is way up high on my board, but look at yours. Did you write down the reaction? So where did the 3 and 4 come from, guys? From my balance chemical equation, which right here is 4 and 3. Okay, just make sure. Mine's way up high, so you guys have to deal with that on your paper. Answer? 4 point what? 14.1 liters of oxygen. Okay, so appropriate sig figs would be what?
14.
Just 14. 2 sig figs, 14 liters of oxygen. Okay, moving on then. So those were some simple ones to get us started to make sure you can see how to use them on map. Now let's go to, can I go forward? Let's get a quick head shake there. All right, so I have a joke after everyone. So long live the heavy metals. Oh, the heavy metals. Mercury, lead, silver's in there someplace. Okay. All right, so consider the combustion of propane gas. Propane. Who's got me here? I heard it. Say again, Caleb. Oh, what was this? Was this 3? No? I thought that's what you were doing. Okay. Combustion of propane gas. So propane means how many carbons? C3H8, because this is an ane. Anes are 2N plus 2 to get your number of hydrogens. All right, so that's propane. Combustion means what, Omar? Plus oxygen. Every time you combust a hydrocarbon, what every single time does it make? So carbon dioxide and water. It doesn't matter if you put water first or carbon dioxide first. I don't care as long as it's both are present. Mikado, how do we always balance combustion? What do we start with? Well, propane's got a lot in it, right? So I told you to start with one element in particular. Oxygens are everywhere. Those are the hardest ones. No, what do you have? Third time's charm.
Carbon dioxide.
No, start with carbon. Just stop with carbon. Okay, just carbon. You always balance combustion in the order of CHO. C-H-O. Alphabetical order. It helps with the balancing at the end. Or you can do oxygen first and just make your life harder, right? Okay, so three carbons. I need 3 carbons. What do I put here? Put 3. Okay. I see 8 hydrogens. I need a 4. I see how many oxygens total in the products. Let's come to an agreement here. So 3 times 2 is 6. So 3 times 2 is 6. And then
4.
okay, so we've got 10 oxygens on the product side because that 3 distributes and that 4 distributes. So 10 oxygens, what do I need over here? Nice, 5 to get 5 times 2, which is 10. We'll work on basic multiplication later. I know you know your multiplication tables. Okay, so in this case, does that balance, guys?
No. Yes.
What's not balanced?
What do you say? I might be really tired.
So there's three times 2 is 6 oxygens, and these 4 times 1. We're doing oxygen. All right, I promise you this is math. I promise. Okay, so we've successfully, very easily achieved our balanced chemical equation. No problems at all. Now we're going to look at the question. So this is balanced chemical equation, number 1. And then we're going to look at our question. What's our given? Blah, 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 blah. 13 grams of protein. Okay, so sometimes you really, read the question, but don't let the reading of the question get you in a tizzy and get kind of confused. Blah, 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 burn 13 grams of propane. Okay, so propane, how do I write propane? C3H8. Okay, and then our question, our unknown, is looking for what in particular? Yeah, so stop there. How many grams of oxygen? Because people like to go, are required to burn? Oh my gosh, I've never heard the question phrased like that. Don't get all in a tizzy. Go, how many grams of oxygen? Stop. Grams O2. That's what I'm looking for. Blah, 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 given. Okay, you don't, if the question disturbs you, look for the 2 pieces you need and don't read the question again. Okay, so I'm starting with my 13 grams. I'm getting 2 grams of oxygen. Look at the mole map and let's plan our process out first. Touch where we are on the mole map. Sorry, I have to keep flipping back. Sorry. Okay, so I'm at where up here? So that's on the moles. We're up here. Hold up. Oh, so many things. All right, so I'm up here at grams of propane. Okay, and I'm going to go to what? Moles using molar mass of propane. And then from moles of propane to, well, what's Y in our question? Oxygen. We're looking for oxygen, right? So we're going from grams of propane to moles of propane. Moles of propane to moles of oxygen, which is our question. And then moles of oxygen to grams using periodic table molar mass. How many steps is it going to take us? 3. So molar mass, mole conversions, molar mass, 3. Now, you don't need that. You don't need the mole map because you know it. It's just this number in the middle that's going to make you use the balanced chemical equation. So, and we're back. Okay, so start with 13.0 grams of C3H8 and multiply by what unit has to go on bottom to cancel? Okay, so I know grams is going to have to go on bottom. Grams of C3H8, you have to write the compound identity out. If not, it's really hard to understand what your grams are referring to. And does somebody have that urine for me? 44.09 something. Okay, cool. So that's 44 grams of propane. Is equivalent to what? 1 mole. So we're talking about this first step was molar mass conversion from moles to, or grams to moles. 1 mole of propane goes on top. This is old school. We've done this for, for 2 weeks. Now, I'm in moles of propane. Nobody cares about propane. Who do I care about? Oxygen. So how do we get from propane to oxygen? Huh, there we go. So we got how many of these? Whoa. 1, coefficients only. This is a coefficient of 1, and oxygen has a coefficient of 5. So my mole ratio here, who's going to go on bottom to cancel? So I put 1 mole of that, and who's going to go on top because I want more information about it? 5 moles of oxygen. So this is coming from balanced chemical equation. So first step, grams to moles. Easy, we've been doing that forever. Moles to moles, we had to use balanced chemical equation. Now we're going from moles to our final. This is a quick reminder, we're looking for grams of oxygen. So how do I get from moles to grams? 32, because it's O2 in this case, remember? So what do I put on the denominator here? Right, so I see this mole needs to get canceled, so I'm going to put 1 mole of oxygen and its mass on top. 32 grams of oxygen. So I went from propane grams, canceled those out. Moles of propane cancel. Moles of oxygen cancel. The only thing left remaining is my grams, which is what my question was regarding. And now you're calculating. like 40? Trying to do it in my head, not too close. 47 point what? 1718. Okay. Process. I'm sorry. I'm looking at your numbers, but I'm not checking your numbers all the time. So we see this. How many sig figs do I need? That is my bad. That's probably like 32.0 something. So 3 sig figs will be rounding this to what? 47.2 grams of oxygen. Okay, so you're just following your mole map, right? It's not, the only thing that's new is that our balanced chemical equation is really important to our reaction at this point, or our balancing at this point. Okay, I'm reading this in blah, blah, blahs, okay? So, how many grams of carbon dioxide? What is that? That's the question, that's the unknown, okay? Grams CO2. I swear this helps you to write it down because it makes you see the end in mind or work with the end in mind. You know you're looking for grams of carbon dioxide. Blah, 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 blah. What do I see? 0.50 moles of C3H8. Okay. So how many grams of carbon dioxide are produced when 0.5 moles of propane reacts with excess oxygen? That excess oxygen is a distractor. It's just telling you some more information about the reaction. I could tell you this happened around some puppy dogs and kitty cats, but nobody cares, right? This happened in my house, but nobody cares. So this is the only thing that matters. Blah, 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 blah. And then this is our only other thing that matters. Blah, 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 blah. Okay? So that helps you. It helps narrow in for the two things you're looking for. All right, so I'm starting off with what, guys? 0.50 moles of propane. All right, guys, I'm already at moles. Halfway there. Okay, so it's right here. Moles of moles of propane. Where do I have to go next? Say it again. What unit? So if I'm already in moles, I can easily get to moles of anything else using the coefficient mole ratio. So what's my mole ratio? So I'm looking at, why am I looking at propane and carbon dioxide? Because that's what the question's asking for. The question's telling you who you're comparing. You don't get to pick who you're comparing. The question says, I have propane, I want carbon dioxide. So I have propane, I have 1 mole of it, and I'm getting 2 carbon dioxide, I have 3 of those. That's how you know who to compare. The question tells you. Okay, so at this point, what am I writing on bottom? Why 1 mole of propane? Because I need to cancel these moles of propane out over here. And that 1 came from what? My equation of 1 up there. Okay, and I'm going to who? So moles of carbon dioxide, and how many of them do I have? 3, according to the balanced chemical equation. All right, so I went from moles to moles. All right, home free. Moles to what now? Grams of CO2, because I have moles of carbon dioxide. I got to get to grams now. So what goes on bottom? Just 1 mole of carbon dioxide. This is old school now. We know that we always compare it to 1 mole. The only time the 1 is in there is only for this BCE mole ratio. All right, so how many grams is in CO2? 44.0 what? 01-ish grams. So that's carbon plus oxygen plus oxygen. That happens to be about the same low amounts of propane. That was just a quinky dink. Okay. So at this point, am I done? What do I have to do? Okay, so I'm going to see that I've canceled units. So moles of propane cancels with moles of propane. Moles of CO2 cancels with moles of CO2. Grams of CO2 remain. I'm good because I'm up here. I've seen that I've met my end. So 0.66 something. .5. I'm with you. Oh yeah, sorry, 66. I'm looking at my decimals. 66 point what? 0.015 grams CO2. And then sig figs. How many sig figs? 2. This one has 2 sig figs right here. Mole ratios are not measurements. This is going to always be our not limiter, so just 66 grams of CO2. Okay, you guys do the last one by yourselves, or talk in your tables. I want to hear you speaking what I think I need you to, or I think I need you to.
You guys are probably using every taker, there's no way you're writing this on a little tiny piece of paper. Actually, let's see. This is the
Do we find the molar mass of oxygen the first time?
what's your given?
The 13.
Okay, so. So you want grams of oxygen? So basically, where are you at here?
Are you?
Yes, you're here. Oh, I got you.
Molar ratio.
Alright, finish that last step you're doing. And I want to hear your thought process from beginning to end here. So, listen, 5, 4, 3, 2, 1. Bradley, what was your given?
Our given was the 13 grams of propane.
Okay, first step, you had to convert where? Grams of propane to
Moles.
moles of propane. Mikado, what was next?
I don't know.
No, listen to us. Bradley, we started off doing what? Listen, guys, I'm not going to keep repeating myself. Ready. So, grams of propane, you went to what?
Moles.
And then Mikado, what?
We went to the ratio.
So, we went from moles of propane to moles of oxygen. And then Will next. Liters of oxygen, we had to use what number to do that? 22.4. And what did you guys get? 30 what? 13.0 liters. I did this with the board blank, so sorry if it's a little messy. 13.0.
33.
Oh, I thought it was 33.
Yeah, I said that.
Is there anybody else got 33?
Yeah.
Okay, that's what I had heard. 0.0? 0.6? So, I love it when you guys misinform me and I have to keep erasing.
32.0.
30?
33.0.
Make a choice. 33.0?
Yes.
I'm stopping there. I'm not erasing again. Okay, so Grams of propane canceled with grams of propane. Moles of propane canceled with moles of propane. 5 moles of oxygen. The moles cancel with these moles. 22.4 liters remain. Yay. Yay. Touch yourselves in the back. Woo. Okay. So you have to show your cancellation units just to ensure that you're good there. Okay. Let's do this one together too. I'm going to have a couple of you guys give me the step-by-step before we even dive in though. Okay. So, actually no, even before, you guys talk about your steps, and then we'll write them down together, okay? Talk about the steps it would take you to get here. All right, Caleb, where are you starting? Propane. Listen for me. Caleb, what do you guys do first? So what goes on bottom? So it was like 44.09 is what I heard earlier, so I'm sticking with my story. Okay, so that's our molar mass in 1 mole of propane. Kaylin, what do you guys do next?
We did 1 mole of propane on the bottom.
Why the 1? Where are we getting this 1 from? From the ratio, right, okay. Keep going. What goes on top?
4 moles of H2O.
Where'd you get the 4 from? The ratio. Where's the ratio at, guys? Balanced chemical equation. Don't forget, those are just the coefficients we're pulling down. And then Cassie, last step. Avogadro's number. Okay, so I hear molecules, right? That means particles, and particles says Avogadro's number. So Avogadro's number is molecules of H2O. Okay, squeezing that on there over 1 mole of water. Okay, everything cancels except for what? Say again? Molecules of water. Okay, so the molecules of water remain. Yes, that's what we wanted. So, what is that? 40 is about 1. So like 5 point something times 10 to the 23rd. 5 point what? 46 times 10 to the 23rd molecules of water. Okay, so if you want to abbreviate molecules, do not put mole, because mole has its own little entity, right? So if you want to abbreviate molecule, you can write MOL''C. Something like that to let me know that you're writing molecule, not mole. Okay? Alright, so the last one that we're going to do is number 3 together. And this one includes that one section of this little chart that I haven't even talked about yet, which is called concentration or molarity.
Attention teachers and students. We need students from the following homerooms to report to the auditorium at this time.
Oh, this is freshman.
Mr. Smith, Mr. Curtis, Ms. Harris, Ms. Cook, Ms. Escalara, Coach Barbie, Mr. Imbergia,
Freddie Mercury.
Ms. Quinn, Ms. Martin, and Ms. Ridenauer. Teachers, if you need to know who these specific students are, you can check the email that I sent out this morning. It includes a list of students and what homerooms they are in. Thank you.
You guys are not in any of those rooms, right? It's supposed to be all freshmen. Okay. Thank you. All right, so this is the only section. We don't know what this is yet, okay? So I have about 10 minutes. I think I can do this with you guys. So we've been using these chemical reagent bottles, and a couple of you guys asked me, you're like, what's that 1 M in the front of copper 2 sulfate? And I was like, oh, it's a concentration. Do you remember seeing that on some of your chemical bottles? Or like 0.10 M iron 3 chloride. You saw these little notations in the front. So if you haven't seen it, you will. But that means concentration. So on Kool-Aid, okay, or sweet tea, it doesn't say, oh, this is concentrated Kool-Aid. You just expect it to be good. You expect it to be normal. You expect it to be the appropriate concentrations. Well, let's say, you know, you're diabetic or you're going on a diet or something. You're like, I should have less sugar in my sweet tea. You get unsweetened tea. Well, basically that's 0 molarity or 0 concentration of sugar, whereas sweet tea would normally have, I don't know, like 10 molar or 10 concentration of sugar, which is like diabetes, okay? So these give me indications for chemicals that are in my bottles. So if I have a lot of stuff that solute copper 2 sulfate in my liquid, it's like 1 molar, 2 molar, 3 molar, 4 molar. So it's exponentially great. It's higher. But if it's pretty dilute, it's like 0.1 molar. The word molar is what I'm saying for M here. So let me actually get some space and I'll tell you what this means. So it does refer to solutions. So write this down for yourself. Molarity means solution concentration. So instead of just saying, oh, it's concentrated or it's not concentrated, we quantify it. We say this is how concentrated it is, because it matters when we're talking about grams and moles and so forth. So if molarity means molar concentration or solution concentration, I have an abbreviation for it. It's capital M. Go figure. We're trying to keep it easy here. Capital M means moles of solute over liters of solution. Molarity, mole, and then larity, mole, and liters. So in the reactions you guys have been doing, it's like take 5 milliliters of this and react with 5 milliliters of this. So SOL in a solution, yeah. So if I say take 5 milliliters of this and react with 5 milliliters of this, there's actually stuff inside of those volumes, and so the stuff inside are the moles that are inside, or the quantities that are inside. So what I can tell you is, oh, guys, you have a 2 molar hydrochloric acid solution. What does that actually mean? That actually means there are 2 moles, so basically the 2 is referencing the moles that are present, 2 moles of HCl in 1 liter of solution. So basically this is the number of moles. And we have another conversion factor. It's used the same way every other one is used. We use it to cancel units. That's it. But if I start you off with 5 milliliters as a given, 5 milliliters and liters, they don't quite match, right? So if I start you off with 5 milliliters, how would I get to liters? Say again? How King Henry died by drinking chocolate milk. So what's our conversion? King Henry died by drinking chocolate milk. Where's liter here? Base, that's liter. Okay, where's milli? Little m over here, milliliter. So who's the bigger unit? Liter. So if I'm converting 2 liters, I'm going to put 1 liter on top, and then what on the bottom? How many? 1, 2, 3. 1,000. Sorry, I was making sure I heard that right. Because it's 1, and then 1, 2, 3 zeros over, so 1,000. All right, so that's how I can convert from milliliters to liters. And then what I can do is I can plug this in right here, 1 liter on the bottom, right? And then it's 2 mole thing on top. And guess what I have successfully done? Gotten to what? Moles. And once I get to moles, I am home free. I can get to anything else. Because the milliliters cancel, the liters would cancel, and I can get to moles, and I can go to mole ratio, or I can go to grams, or I can go to atoms. I can go to anything from moles. So this is just an extra way to get to moles. It's just mainly only in solutions. We don't do liters of solution like we do liters of a gas. So you hear the differences there, right? What number always comes into play with liters of a gas? 22.4. Okay, so that's a standard number. Liters of gas, if it ever says gas, when you recognize it as a gas, you must use the 22.4 liters per mole. But if it says liters of solution or aqueous solution, you're using those type of liters, which is liquid liters, not gaseous liters. So that's just a dichotomy, like you keep separating your head. So we're going to probably only do one part of this next one. And, oh, sorry, here. All right, single replacement reaction between magnesium, copper, 1 chloride. Write the reaction out. Magnesium, how do I write that? Mg reacts with, how do I write that? CuCl, right? That's because it is copper 1, crisscross your 1 over, chlorine over 1, you're good. Yields, what kind of reaction is this? Same replacement. Does magnesium, oh sorry, magnesium is the free one, right? Double check. Is magnesium active? Super duper active. It's high on the list. Copper's really low, so they will switch. So what does magnesium pair with? To make MgCl2, because the magnesium charge crosses over, and copper gets booted to the cold by itself, lonely. Okay, so balance. I know, balance.
2 in front of the copper chloride.
2 in front of the copper, 1 chloride, and into the singular copper metal. Okay, so balance chemical equation done. So here's where this is going to be your telltale sign. You're using molarity. It says a solution, 500 milliliters of a 0.4, what do you call the M again? Molar solution of copper 1 chloride. That is actually your given information right there. It's 2 pieces. I'll show you how to tackle those 2 pieces. Okay, blah, 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 blah. How much copper will precipitate from the solution? That's our question. So if our question is much copper, much generally means like collecting in the mass form. What unit is mass? Grams. My question is looking for grams of copper. My given here, that together gives me moles. Always. So here's your tip for yourself. If you ever have those 2 things together, you just do molarity times volume to get moles. Molarity times volume to get moles. Because what's molarity's units? You just write these down. What are molarity's units? Say again? Moles per liter, right? So if you take moles by liter and you multiply by volume, let's just say volume's in liter form, what cancels? Liters. And what remains? Moles. So if you can take your molarity times your volume, this is exactly what you're doing. The moles stay with you. And remember, if you once you get to moles, you're home free, you can go anywhere. So let's try this one. So all of this is going to be wrapped together. So 500 milliliters, how many liters is that? 0.5 liters, right? And I can do that in my head or I can write this down. So I'm going to write it down for clarity's sake. 1,000 milliliters is equal to 1 liter. So that, again, is 0.5 liters. Okay, now I can take M times V. So I'm going to write it down here, okay? So 0.40 molar, which is moles per liter. I'm taking this right here, moles per liter, multiplying it by liters. How many liters do I have? So 0.5 liters. Those cancel. Oh, moles of what? Sorry. Copper 1 chloride. Okay. Now, I've canceled liters here, but moles are still right here, right? Who do I want to get to? I'm in copper 1 chloride. I want to get to who?
Copper.
Just plain copper, because that's what this question here says, right? All right, so I'm going to stretch across this. I know these moles have to go where? Down. They go down. Moles of copper 1 chloride go on bottom. And I'm doing mole ratio because I'm already at moles, right? Moles of A go to moles of B, or moles of apples go to moles of oranges. Moles of copper go on top. Now, what are these numbers, though? Where are you getting this number from? Who gets the 2? Both of them, actually, yeah. 2 copper, 1 chlorides, 2 coppers. Wonderful. Now, don't write 1 and 1. I want to know that you know where your numbers are coming from. 2 and 2. So 2 moles of copper, 2 moles of copper, 1 chloride. That cancels with that. Last step, give me the grams. Molar mass, give me it before we go. Okay, so I will update homework on the website. You guys are responsible. Wait. Where it says you try, you are trying those 1, 2, 3, 4 examples. That is all you're doing this weekend right now. Okay? Unless you have other work that you need to finish up. If you have problem sets, requests, or anything like that, please turn them in. Notes I already saw. I went around. I'm gonna mark you as complete. Yes.